Hello friends, the topic for today is shapes of atomic orbitals, boundary surface diagrams for S, P and D orbitals. The topic has been taken from Atomic Structure of Class 11. So the plots of total probability densities for 1s, 2s and 2p can lead to the shapes of atomic orbitals. These are shown with the help of boundary surface diagrams in space. These are the boundary surface diagrams for 1s and 2s orbitals respectively. The boundary surface diagram generally encloses a region or space where the probability of finding the electron is very high. The electron density is very high, about 90%. So the shape of S orbital. The S orbital is present in the S subshell, and for S subshell the value of L is 0, as ML is also 0. So there is only one orientation which is spherical in shape, and in this there is a uniform electron density around the nucleus. The probability of electron is maximum near the nucleus and decreases as we move away from the nucleus. The 2s orbital in comparison to 1s has a bigger size as compared to 1s orbital because it belongs to a higher energy shell, second shell, 2s. And you will also see that in this 2s orbital the probability of electrons is here in this region, but here it is 0. This region, it is called node, and the number of nodes in an ns orbital is related to the quantum number. The total number of nodes for an ns orbital will be n minus 1 nodes. Ns orbital has n minus 1 nodes, and number of nodes increase with increase in principal quantum number. In 1s orbital, n is 1, so 1 minus 1, n minus 1. 1 minus 1 is 0. So 1s has no node. You can see that there is electrons probability in the whole boundary surface diagram, and there is no region where there is no electron. Whereas in 2s orbital you see one node. In 3s orbital there will be 2 nodes. So in case of a 3s orbital, the diagram will be this is probability, one node, then probability, then node, then again probability. So there will be 2 nodes in 3s orbital. Shapes of p orbitals. Now p orbitals are present in p subshell, and for p the value of L is, angular quantum number is 1. So ML will be from minus 1, 0 and plus 1. So there will be 3 orientations, 3 orbitals, and these orbitals will be having, and they'll be designated as px, py and pz depending upon the axis along which they are directed. So unlike for s orbital, which was spherical, the p orbital boundary surface diagrams are not spherical, they are dumbbell shaped. Px orbital, the dumbbell is directed along the x axis. In py orbital it is directed along the y axis, and in pz orbital it's directed along the z axis. You will see that for every p orbital there are 2 lobes, and this point is the nucleus. Here the probability of finding the electron is 0, and if a plane is passing through this point, then this plane will have no probability of having any electrons. So this plane is called nodal plane. So for a p orbital, these two are the lobes. This is the nodal plane, and These three are the axes along which any p orbital may be directed. For example, here it's directed along the x-axis. Then similarly we can have around the y-axis and around the z-axis. So as this p orbital is directional, it also influences the geometry of the molecules, which involve the participation of p orbitals in them. So if p orbitals are participating in bond formation, they will influence the geometry of the molecule. For example, for a molecule where 1s and 3p orbitals are combining, the geometry will be tetrahedral, and so on. We will do this later on in chapter number 4, chemical bonding. So the orbitals having higher values, these were the diagrams for, let us say, 2p orbitals, 2pz, and the orbitals for higher values of n, they will be having similar shapes, but the sizes will be bigger one. So 3p orbitals will be bigger in size than the 2p orbitals. The orbitals belonging to the same energy shell will have the same energy, and these are called degenerate orbitals. So px, py and pz all have the same energy, so they are called degenerate orbitals. By convention, we have different ml values. By convention, we generally give pz a value of 0, and for px and py +1 and -1 respectively, but this is not fixed, and there is no hard and fast rule as such. D orbitals are present in the d subshell, and d is found first time when n is equal to 3. In the first shell and second shell, there are no d orbitals. So in the third shell, n is equal to 3 and L is equal to 2. And when L is 2, it is d orbital, and the ml values can be -2, -1, 0, +1 and +2. This means that there are how many? 5 orientations leading to 5 different orbitals. And these 5 orientations are designated as dxy, dyz, dzx, dx square minus y square and dz squares. All these 5 have the same energy, so they are in the same degeneracy state, or all 5 are called degenerate orbitals. Out of these 5, the dz square has a donut shape and a ring around it, but the others 4 all have clover leaf shape. The 4d and 5d orbitals will also have similar shape, but again they differ in energy and size, and their energy and size are greater than that of 3d. How to why? You will find that there are 4 lobes, and these lobes are present in the xy plane. So there are 4 lobes, one between x and y, and similarly the other between again y and x. For dyz, the shape will be similar, but it will be between y and z axis. This was between x and y, this will be between y and z. And dxz will be between dx and z. Now dx square minus y square also has cloverleaf shape, but here it is not present on the plane, it is present on the axis. It's present on the x-axis and on the y-axis. And dz square orbital has a donut shape with a ring. Number of nodes, let's talk about the number of nodes. These kinds of nodes were called radial nodes, and this is the nodes which are present on the plane that is passing through this. This is called angular nodes. So besides the radial nodes, probability density function is 0 in the radial nodes. The probability of density function for P and D are also 0 at the planes. So for P orbital there is only one nodal plane where probability is 0, but for D orbitals there are two nodal planes where probability are 0, and in all the total nodes present in any orbital will be the sum of the angular nodes and the radial nodes. So for radial nodes, you know, the formula was n-1. For angular nodes, planes where the probability of finding the electron is 0, which passes through the origin or nucleus, these planes are called angular nodes. They are given by L, which has usual value, that is 0 for S. There will be no plane for S. Then P will have L value 1, so there will be one nodal plane where probability is 0. For D there are value is 2, and similarly there are two planes where probability is 0. The total number of nodes for an orbital will be n-1. These total number of nodes are sum of angular nodes and radial nodes. It's all about the shapes of orbitals.